Hi there, Bruce Kingsley here. Wanted to give you an update on my Ultimate Throttle project. Ultimately, the project is based off of emulating this throttle here. The standard LocoNet type throttle that I use on my model railroad. But with a twist, I wanted to operate the locomotive similar to when I rented a pair of locomotives from the Western Pacific Railroad in Portola, California. After having that experience, it's just not the same, with a handheld item. The feel, the sounds and so forth that came from the real locomotive just really stuck into me. And I thought, how could I go and emulate? So I'm going to give you a quick preview of what I call my bench work of my throttle and its progress. Everything you'll see in here is the sound it is. So let's start going over the basics of what this whole thing is all about. So again, what we're doing here is we have to emulate a standard LocoNet DCC throttle. That can, would go into your normal LocoNet jack and operate like this, but without dials and buttons, but the real controls. For the control panel, I'm using standard industrial switches. Even so, the power that's going through this is, in the milliamps. The gauges were originally real pneumatic gauges that I removed the internals, and there are small RC motors behind them. The control panel's load indicating meter, it's just made from scratch, styrene. There's just a copy of a real control meter indicating meter. The throttle, which is made from round aluminum stock that one of my friends here locally who has a machine shop in his basement was helping me to machine. This has the notching devices in here and includes an interlock system. The interlock includes a solenoid that down here you can see that's got a wedge shape, which keeps the operator from going past one notch at a time. There's a homemade sensor on the back of it that detects the notch wheel attempting to go out, which will go to the computer to determine if it's really allowed to allow it to go out of this notch and into the next. The reverser, which is an industrial 3-position switch, again just low current going to the computer. The engine brake, which is rotary, and this is the emergency brake. It has a variable potentiometer on the bottom and a limit switch that detects the downforce of the handle for an emergency. The bell, another industrial switch, made a different type of handle, so it's more like the prototype. Certainly wouldn't be complete without a horn. This is simply a cord and goes through some springs and a limit switch to leave more of a feel. So now that we've gone over all the control items, let's go and look at the electronics that are going to be behind this throttle that'll make this all come together. Then we'll run it. So I'll quickly go over this. Again, I'm not going to go into a lot of details here. That can be on some future information. So this is the brains of the throttle. I need to point out first that the PC over here is not running this throttle. It is used for programming the Arduino computer, and right now I have it set up as a monitoring program. So as the electronics are running and I'm monitoring the LocoNet activity, I can view it. I do use JMRI software to run my model railroad, which does include the throttle and software that enables you also to talk to LocoNet. But I felt that some of the flexibility and not tied to a computer I wanted a lot more independence, so I ruled using this out. The brain behind this entire project is actually underneath this board here, which is an Arduino Mega board. For those who've never seen, this is it. This is one of the larger versions of the Arduinos. You can get them quite a bit smaller than that, but I needed a lot of I/O and memory, and I needed more serial interfaces. Additionally, we have power supplies, we've got some sound, tone, and bass controls. We have our decoder. You can see it sitting right here. This is an ESU Lock Sound version 4, which is a very specific type, which enables you to do your own programming. In this case, I did a lot of modifications to it, including both how it operates and put a lot of my own sounds that I recorded while I was at Portola. I still need a motor on it because I need to drive it, and at the same content I wanted to be able to pick up speed and so forth. So I have a little tack that's on top of here as well. Now the decoder is connected up to a control station. In this case I'm just using my old Zephyr from Digitrax, though this is not being used as a throttle. In this case I'm just using it as a control station. So I have a way of running it to the rails, if you will. Equally, this connection right here, this is where the connection would go to the throttle jack on the regular locomotive layout. I have some optically oscillated relays that are connected to the Arduino, and these are used for running everything from the solenoid to some of the light indications. Now, a lot of the lights actually have LEDs behind them, and it could have been driven directly from the Arduino. I chose to stick to the relay because it also creates the sound. One of the components of this system here that was the magic of letting this all come together is this little board right here. This is made by RR-Cirkits. This is their product Local Buffer USB Revision N, which is a very significant. This product is sold with the prime purpose of connecting your PC through this USB and be able to connect up to LocoNet. I was very fortunate that the owner of this company spent a couple of hours with me on the phone trying to come up with a solution for me to connect my Arduino up to LocoNet, and with some modifications that he worked through to me, I was able to go and do that. Finally, the other boards are different amplifiers, mixers. I have a Dream Player Pro stereo sound generating board that I use for sound effects. And finally, all of this gets fed to a amplifier and speakers dedicated to this. This is a Logitech system made for a computer, and it's rated around 200 watts for the subwoofer. To really feel it, on the bottom of the control chair, I have a butt kicker tactile transducer, and this is powered by its own 250 watt amplifier. So we've got about 500 watts of audio sound going here. So enough talk, let's start showing how this goes. So again, lots more to do on this thing, but it'll give you a good idea. And the sounds that you're hearing are what's coming out of the speakers. So I've got a lot of the rules built into the software to try to make it run as realistic as I can. We have an engine that's been sitting here for a while, error indication in case we have no air in the reservoir. For debugging purposes, I have an alarm that goes off that tells me when I'm doing something that's wrong or something's wrong with the software. The bell's ringing because it's telling me that I don't have enough pressure to run the horn. So let's get this baby going. So we can go and get the fuel and oil coolers going. Now the engine's been sitting around for a while. We don't want condensation in the cylinders and damaging that. So let's turn it over a little bit. Let's go and blow those cylinders out. So let's start her up. Now what I'm going to do is I'm going to purposely not start it properly. Now I'm going to start it but let go before the engine actually catches on. So in this case, I didn't hold it long enough, engine didn't catch on. Sounds like somebody wants us to get this train moving. Okay, now we're running. And the first sound that you hear is the compressor. It knows that we're low in pressure. And immediately starts. So even, I don't have these gauges calibrated or so forth, you can actually see the gauge is still going up as we're building up pressure. The light indication went off because it saw that we had at least the minimum pressure that we needed. Even my current amplifier shows some current. It's not correct. I am still working on the algorithm that calculates the current draw based off getting the engine moving either aggressively and the effects of low current when we're coasting. So now that we have enough air pressure, we should have some horn. And I might add that anytime we use anything that uses air, we're going to lose some air pressure, and at the same content, it'll build back up. I have a dump valve here, so if I want to test that, I can purposely, and I'm not going to do it right now because we're going to hear the air compressor kick back on again, but I can purposely dump it to verify that that activity is going on. So we can go and put it into forward, put the transition into it, and one thing I might add is I'm going to take it back, put it in neutral, and I'm actually going to go and just notch it. So we get our sound. Now one thing I'll be pointing out is that while I'm notching this, since I do not have it in forward, I still have an idle, I can notch the engine, but if you can see, the motor's not moving. Okay, so this time we will operate. So we got we go to our notch. Release the brakes. You can see the motor is going. Even if I go and apply some brakes, you can see we stopped the motor. I did it kind of aggressively, so we got a squeal out of it. Release the brakes more and get the back going again. Notch it up. Bell on. Actually to a stop, use the brakes. Now do aggressively. Squeal the brakes again. One of the details I wanted to add was wheel slippage. I saw when I was going through the manuals. And so that can be reproduced the same way. You can go and notch up. And then we'll say we overly aggressively notch. Bring up our RPM faster than it likes to see, and we can see our wheel slippage indicators coming on. I'm already going over. I'm turn the sander on. In fact, I'm drawing a lot. I'm almost at the max current. turn the engine off. And I still have some reservoir pressure. Gone, indicator on. So that's it for now. I'll do updates as I get completed, and at the same content, I have another virtual tour I need to get back to as well that I'm well overdue on, that I promised to do. So, happy model railroading!